In this video, we're going to be practicing going from chemical name to chemical formula. So our first example, rubidium sulfide. To do this, first we identify what kind of compound we have. Rubidium sulfide. Rubidium is a metal. All right, it's element Rb. Sulfide is a nonmetal. And so what we know is that we have metal, we have nonmetal, therefore this is ionic. So we look up on the periodic table based on the position of these elements if we know their charge. And in this case, we do. Because of its placement in the first column on the periodic table, rubidium has a +1 charge. So we mark that. Sulfide, because of its placement, we know it has a 2- charge when it's an ion. So we mark that. Now, once we have those identified, we cross the charges. So the number in front of the plus sign, the number in front of the minus sign get crossed. And once they're crossed, those give us the subscripts now on the actual compound, which would be Rb2s, rubidium sulfide. Now, strontium nitride. Again, we approach this the same way. Strontium, element Sr, is a metal. Nitride, element N, is a nonmetal. Therefore, this again is ionic. Strontium, because it's ionic and is in column 2, the alkaline earth metals, has a charge of 2+. Nitride, the nonmetal, in its column, when it's an ion, has a charge of 3-. And therefore, we cross the charges again, the 2 and the 3, to determine our subscripts. And so we get the final formula, Sr3N2 for strontium nitride. Now, calcium carbide. Calcium, element Ca. Carbide, carbon, element C. Calcium is a metal. Carbon is a nonmetal. So again, this is ionic. This is binary. And so from its position in column 2 on the periodic table, calcium has a charge of +2. Carbon, from its position in the periodic table, when it's an ion, has a charge of 4-. Now again, I cross the charges. So I take the 2 from the plus and the 4 from the minus. I cross them. And that then gives me Ca4C2. Now, these subscripts are meant to indicate how many of each is necessary, each ion is necessary to make the overall species neutral. And for ionic compounds, when we have this, we always reduce the subscripts to the simplest whole number ratio. In this case, this isn't it. In this case, this can be reduced, and we write it as Ca2C. All right, let's do some more examples of different kinds of naming now. Now we're in type 2 naming. And in type 2 naming, the first one we have up is copper 2 oxide. So, first off, copper. Copper is element Cu. Oxide, oxygen, is element O. From its position in the periodic table, we know oxygen, the nonmetal, and copper is a metal, the nonmetal oxygen has a charge of 2-. Copper is a transition metal. We do not know its charge, but in the name it tells us the charge. It tells us the charge is 2. It's a metal, so that charge has to be positive, so the charge in the copper is 2+. So again, like before, we take our numbers, the 2 and the 2, we cross them like we did before, and so what we end up with is Cu2O2. This is an ionic compound, so it needs to be reduced to the simplest whole number ratio. So we reduce this to CuO, copper 2 oxide. Iron 3 sulfide. Iron is element Fe. Sulfide is sulfur atom, S. Metal, nonmetal. This is a binary ionic compound. Sulfur in an ionic compound has a charge of 2- from its position in the periodic table. Iron is a transition metal. Again, we don't know its charge from the periodic table, but it tells us in the name that this is Iron 3, it's metal, so it's always positive, so that 3 means that the iron has a charge of 3 plus. So again, we take our numbers, we cross them, and we end up with Fe2S3, iron 3 sulfide. Now, moving on to our next type. Now I'm going to include the polyatomic ions, which you should be memorizing or have already memorized. Copper 1 chlorate. Again, copper, element Cu. The 1 tells us its charge because this is a transition metal. So this is a +1 copper. Chlorate, from having memorized the polyatomic ion table or looking it up while you learn it, chlorate is ClO3 with a negative charge. So, again, I take my numbers in front of my charges, the 1 that's in front of the plus, the assumed 1 is in front of the minus, I cross them, giving me Cu1 ClO3 1. But you don't write the 1s, obviously. Manganese 2 nitrate, manganese, element Mn. This is, again, a transition metal, so it tells us the charge is 2. And that tells us 2 plus because it's a metal and it's always plus. Nitrate from our polyatomic ion table is NO3 with a minus charge. So again, I take my numbers, since this is ionic compound, my number there that's assumed, I cross them. So this tells me I need 1 manganese, so Mn, you don't put the 1. I need 2 nitrates, and to indicate that, I put the NO3, because that's nitrate, in parentheses, and put the 2 that I just crossed outside the parentheses like that. So MnNO3, 2, manganese 2 nitrate. Now let's look at some binary covalent compounds. Our first example, disulfur dichloride. These are basically one of the few kinds of non-metal compounds we're ever going to name. And so they're going to be binary, and so we know we're basically looking for atoms and how many of each we have. Sulfur, element S. How many? Di, 2. Chloride, chlorine, Cl. How many? Di, 2. So S2Cl2. Carbon tetraiodide. Carbon C. How many? Well, there's nothing written there, and we know that means there's 1. Tetraiodide, iodide, iodine, I. Tetra, 4. So Ci4. Diphosphorus pentoxide. Phosphorus, P. How many? Di, 2. Oxide, O. Oxygen. How many? Pent, 5. So P2O5 is diphosphorus pentoxide. So here we have some acids. And one thing all acid names have is the word acid. And one thing we now know is that when we see acid, at least for the scope of this class, that means the compound as H+. So we can put our H+ as our cation in each of these examples. So now we're looking for the anion, and that comes from the main name of the acid, iodus, acid iodus. Iodus, the OUS, as we learned in class, comes from the polyatomic ending ITE. So this was iodite, and iodite is IO2- from our table of polyatomic ions. And so we now know that we take the 1 that in front of the plus, the 1 in front of the minus, we cross them, we cross our charges like we've done over and over again, and we end up with iodous acid, HiO2. Nitrous acid. Again, nitrous. OUS came from ITE, as we learned, so nitrite, the polyatomic ion nitrite. Nitrite is NO2-. So again, we take our assumed 1 in front of the plus sign, our assumed 1 in front of the minus sign, we cross them, and we end up with nitrous acid, which is HNO2. And finally, hydrobromic acid. So in this case now, we have the word hydrobromic. Hydro tells us that this the species, the anion, does not contain oxygen. That's what hydro means. So I'm looking for a bromine ion that does not contain oxygen. And what is it? Well, it's just bromine, the element. And as we know, in ionic compounds, which acids are for the scope of this class, bromine, the ion, is Br minus. So when I cross the charges, the assumed one in front of the plus sign, the assumed one in front of the minus sign, cross them, I end up with HBr, hydrobromic acid. All right, now that we got through that, we can try. So now let's look at how we just do these, a bunch of these all thrown together, all mixed up, and how we identify what we have and how we get the name out of it. So, chromium 6 sulfide. Chromium, element Cr, is a metal. We know 6 tells us its charge, 6 plus. Sulfide is a nonmetal, sulfur. From its position in the periodic table, we know its charge, 2 minus. So this now tells us we have a binary ionic compound. We know binary because there's 2 elements. We know ionic because we have metal and nonmetal. So again, I take the numbers in front of the charges, the 6 and the 2, I cross them, and what I end up with, Cr2S6 can be reduced to CrS3. Remember, you only reduce ionic compounds. Never, ever reduce covalent compounds. Chlorous acid. Acid tells us H+. Chlorous tells us we have the ion chlorite. Chlorite is ClO2 minus from our polyatomic ion table. Again, we cross our charges, the assumed one in front of the plus, the assumed one in front of the minus. Those get crossed, and we end up with HClO2. Lead 4 carbonate, lead, Pb. I know in this case it's an ion because it tells me the charge, 4 plus. Carbonate. Carbonate is a polyatomic ion, and it's CO3, 2 minus. So again, we take our our numbers in front of our charges, the 4 and the 2, and we cross them, and we end up with Pb2 CO3 4. That can be reduced, and needs to be, to Pb CO3 2. More examples. Perbromic acid. Acid tells us H+. Perbromic. We know that ic comes from 8. And so what we're looking for is perbromate, the polyatomic ion perbromate. Perbromate is Br04 minus. So now we take our assumed 1, our assumed 1, we cross them, and we end up with HBr04. Dinitrogen dioxide. Nitrogen, N. How many? Di, 2. Oxide, oxygen, O. How many? Di, 2. N2O2. This is nonmetal nitrogen with nonmetal oxygen. This is therefore covalent, therefore we do not reduce the subscripts. Hydrochloric acid. Again, acid, H+. Hydro. This tells us that the anion does not contain oxygen. So I need a chlorine species that does not contain oxygen. Well, what is it? It's chlorine. And chlorine, from the periodic table, in an ionic compound, has a charge of -1. So again, I take the assumed 1 there, the assumed 1 there, I cross them to get the subscripts, and I end up with hydrochloric acid, H1Cl1, and I obviously don't write the 1s. And finally, ammonium acetate. Ammonium is a polyatomic ion, NH4+. It's one of the very few polyatomic cations. It's the only one you really need to know. And acetate. Acetate also a polyatomic ion, C2H3O2 minus. So I take my ionic charges, the numbers, the assumed one and the assumed one, and I cross them. And I end up with ammonium acetate, NH4, C2, H3, O2.